Okay, hello everyone. Good morning. Uh, I think for for chapter 11, we have arrived at the 11.2, which is the series, and we will move to 11.3. So I hope you can at least uh, you can distinguish or you know the difference between the sequence and series. Okay. So as you can see here, the series, it has the summation, okay, the sigma, like this one. And we have several methods to check whether it is uh, the series converge or diverge. Okay. Oh, okay. Let me just remind you uh, the, the test for divergence. Actually, this is still in 11.2, but I just want to review. So this is the first test that you can use for testing the series. So if series is convergent, then and let the Sn, this partial sum, is A1 plus A2 plus until An, and An is Sn minus Sn minus 1. If converge. It's proving. Okay. So the very first test that you have in the chapter 11 is it's called the divergence test. So whenever you have the series, if you know that the series is converged, then the limit value of the sequence will be 0. Okay. And below is the proving. We can use the partial sum to prove, and using the n-1 as the order. So when the n-1 getting infinite, as the number getting larger, then the both value will be approaching the same as, in which means we can conclude that the limit value for the sequence will be 0. Okay. Let me write some conclusion. So if limit or limit if the sequence, the limit value is not 0 or doesn't exist, then is diverge. So directly you can conclude that the series will be diverge. For example, okay, if you look at the example, series of, we have n squared over 5n squared plus 8. Okay, is it converge or diverge? Yeah, it's diverge. But if you are, for example, getting rid the sigma, the sequence is converge. Okay, you know the difference. Okay, series and sequence. But in series, because, okay, let me write here, because limit as n approaching infinity of this, it's equal 1 over 5, which means the limit is not equal 0. So the series diverge. Okay. The sequence itself is converged, but because it's asking the series will be diverged. Okay. So how do we make this? It's good if you understand the concept, but if you still confusing, maybe difficult to differentiate, remember that the series is additions for some numbers, right? Or number that going to infinity. Okay. So if the sequence converges, if you plus all of the sequence that converge, will it be converged or diverged? It will be diverged, right? It's going infinite, right? Like 1/5. If you plus 1/5 until infinity, can you approach some numbers? No, right? That's why it's become diverged. Okay. But when you have the limit is getting closer to 0, when you plus them, you still have some number because it's close to 0. Okay. Get the logic. Okay. Yeah, that's the uh, test for divergence or divergence test. The very simple test to just knowing whether the series is converged or diverged. Okay. Just using limit and find the limit of the sequence, whether it's 0, whether it's having some number, or maybe going to or doesn't exist the limit. It can be at least 3 solution, and you can conclude from there it's converged or diverged. Sometimes you can, because there will be several methods in chapter 11. So this will be the very first method that you can try because it's not too difficult. It's the easiest method. So test for divergence. Okay, let's move on to 11.3. This is called integral test. Okay, let's observe the series. One over n squared. If you remember, uh, at the chapter 7 on the calculus 1, we discussed the functions 1 over x squared, right? And we discussed the integration of 1 over x squared from, let's say, from 1 to infinite, right? Dx. Okay. So we are going to have a similar approach. Let me draw first the n and the graph for the area on the curve. Let's say this is 1, 2, 3, 4. This is n. I think it's wrong. I think it should be. Okay, the red color means the area under the curve. Okay. The rectangle, this rectangle. Okay. So from the calculus one, we also have proven the sum of the rectangle. This is, let me write one more time. Okay, so remember from the uh, calculus one, the improper integral. So we can use the limit, right? And then maybe using the other variables. And what is the integrations? Or let me write down here. So this is from 1 to infinite. So if we exclude, so let me write here, if we exclude the first term, so if you try to integrate this become right, and you can say that this is t this becomes 0 and it's 1. Okay, now we have this equal to, right? Okay, remember the limit. The limit means it's closer to some value, right? So actually, this 2, uh, the actual number is less than 2. The actual sum is less than 2. And in other formula, but I will not show you how, it's actually this part is pi squared over 6. Uh, it's another Euler formula for 1 over n squared. But from here is actually pi squared over 6 is not equal to, right? Okay. So what we can do is we can approach the number of 2, but in reality, it's less than 2. Okay. And it's related to here. Okay. Let me give you notes here. Because we have gap here, right? Okay. So the more smaller gap the number will be getting too close to 2. But it's always less than 2. It's never exactly the same. Okay. So what is really happening is integral test is um, is only approaching the ideal number. Okay. So to, to emphasize this, I'm writing here that the actual value is different. Okay? But we still can use the integral test to test the convergence or divergence. Okay. But remember, this is not the real same value. Okay. Okay. Now let's see the other example. This is 1 over n squared. Other example is 1 over square root of n. Okay, for example, we have 1 over square root of n. Okay. Now remember that we have p test in the calculus 1. The same p test can be used for the integral test in the series. So when you have 1 to infinity from square root of x dx, the p test is x. So when p is less than 1 or less equal 1, the conclusion will be divergent, right? Divergence. Wait. I think this should be wrong picture. Should be here. So the left picture here, it's underestimate. It's the rectangle is under the curve. Okay, but the right one, if you try to calculate and check the number, it's actually overestimate. So the 1 will be here, 2 will be up here. So the gap will be this gap. Okay. Now the integral test, let me write the theorem for you first. Okay, suppose the function is continuous. It's positive. And this is the most important thing in the integral test. It's decreasing on 1 to infinity. So the series will be converged if and only if the improper integral of 1 to infinity of fx dx is convergent. So if converges, then the series converges. And if this is diverged, then the series also diverges. Okay, so if the integral of the fx dx converge, the series also converge. But is it the same value? Not exactly. Okay? Not that exactly the same. Okay? But it's the same converge. Okay? And if it is diverse, it's also diverse. And to know when you can use the integral test, you need to test the function. Okay, you need to make sure that the function is continuous, of course, positive, and the important thing is decreasing. Okay, so it's always going down. So you need to check the functions first. If not, then you cannot use this method. How do we know the functions is decreasing? Of course, you can try some number, but if the function is really complex, how do you test the function? How to know the decreasing, whether it's decreasing or increasing? Use calculus 1, okay? The first derivative, okay, is less than 0 or greater than 0. Okay, example, test the series. Let's just try this one. Converge or diverge. Okay, you need to prove that this is continue, positive, and decreasing. But it's not necessary to write on the exam, okay, this is continuous positive. But you need to just to prove that, okay, it's decreasing. Okay, and if you know that it's decreasing, you can use the integral. Okay, what is the integral of 1 over x squared plus 1? Hmm? Yeah, yeah, arctangent. Tangent inverse of x. So this will be pi over 2 minus pi over 4, pi over 4. Because it has certain value, so we can conclude that this is converged. And some notes for the p-test or p-series. Actually, it's the same notes for the chapter 7. If you have 1 over n with the power of p, you can conclude this is converge or diverge if p is greater than 1, if p is less equal 1. Okay, any questions from here? Another note for 11.3 is because we are approaching the improper integral. And if you see the integral, it is having gap, right? Under the curve, or the underestimate or overestimate, it has a gap. The second thing we can deal with is the approximations or the estimation, okay, or finding the error, okay? Because this value, this pi over 4 here, we know it's converged, the integral is converged, but it is not exactly the value for the series, okay? And how do we know the series? We can approach them with certain approximations, okay? So let's move to the approximations. So estimation of sum. So from integral test, it can show that the series is converged or diverged, okay? And then how to estimate or approximate the sum. The sum we can approximate with limit, of course. Let's say the estimate value is s. Now the questions also arise that how good the estimation is. In this case, we are talking about the error. Okay? In the series, the terms for the error, usually we say it's the remainder. The same name when you define in the polynomial, you have the remainder, right? If you want to find a factor and it's when you divide it's not completely divided, it's resulting something left on the equations. You call that something that left by is the remainder. Okay. In the series, the remainder is defined by the difference between the S and the Sn. And we can expand this, become the sequence. So this is the error when Sn is used as an approximation to the total sum. Let's say we have another graph here. Let's say this is n. This is n plus 1, n plus 2. We can write down the Rn. This is always less or equal and similarly, if I added the the overestimate, let's say this is the overestimate. So Rn can be under the curve or over the curve, underestimate or overestimate. So we can also say that the Rn it can be also greater or equal the fxx. Okay. Let me write some notes here. Suppose let's say we have some k equals some sequence. F is continue, positive, and decreasing. And sum of the sequence is converges if the Rn is equal as minus Sn. You can write down this one. Okay, but perhaps it's a theory, but in actuality, in the practical way, it's not too complicated to apply. Let me give you the examples. Okay, so if we approximate one over n cubed, let's make it bigger. Approximate this series by using first 10 terms. So meaning the n is equal 10. Okay. First, what we can do is using integral test. So we need to find the formula for the series. Okay. Okay. Just integrate regular integrations. We have and okay. So from here, we conclude that this is equal this formula. Okay, from integral test. So the sum for the first 10 terms, okay, we can write one, two, until 10 cubed. if you calculate this, it's around 1.1975. Okay. Now, this is the, let's say, the real value or estimate, and this is uh, what we need to the comparison. Okay. So the R10 should be less equal. Now the remainder is from the integral test, which is 1 over 2 n, n squared, sorry, n squared, or 1 over 200, or it's around 0.005. So this is the error. If the question is asked, how many terms required for accuracy or for the error within, let's say, 0.0005. We need to just reversing the formula. Okay, we reverse the formula. The remainder should be less or equal this. Same formula. So we can write down this 1 over 2n squared. Now it should be less than 0.005. And we get the n squared, or should be greater than, and it should be, or it's around 31.6 or 32 terms. Okay. So this is the other question that might comes up with the estimation. So the first one is finding the error, finding the remainder, how big the error will be. And the other questions is how many n required for some error. Okay. And we need to just reverse the findings. So the idea is just using the integral test to finding the R. Okay. So the total sum, we can write down plus minus the error. another way to look at the estimations, aside from, let me write uh, the formula. So it can be overestimate or underestimate. Okay, so it's either you can use the left part only or only the right part. Okay, so it can be less, it can be over, because error can be positive, can be negative, right? Positive, negative error. Okay, and because Rn is actually the difference between S and Sn, we can write the terms in the S and Sn. So Sn plus, so both sides added by the Sn. Okay, at least understand the concept, okay? And probably the exam, if this comes up with some certain of value, um, it will be either the concept or the value will be, uh, because usually error having really in decimal forms, right? So I need to try to find a way to make it easier to be calculated. Okay. So these terms, you can use the left part or the right part. And that's the 11.3, okay? The integral test and the estimation sum. So the important thing is the integral test. If you can uh, prove that the series is decreasing, always decreasing from 1 to infinite value, we can use the integral test and find the converges or diverge, find the series. But again, it's the task, how we are going to choose the task or choose the method. It depends. It depends. It's actually up to you. You can choose whichever you prefer. Okay, any questions? Okay. I will move to 11.4 and maybe finish the 11.4, and then we can finish the class. Okay. So 11.4 is the comparison test. Okay, now to begin the comparison test, now look at the series. Okay. 1 over 2 with the power of n. Okay. Is it converged or diverged? What kind of series? What kind of series? Converged. Yeah, it's converged. Okay. So what kind of series? You can write the first few terms. For example, 1 over 2, 1, right? 1 over 2. Okay. And you can think this series as, okay, maybe actually I'm multiplying with half, also half, right? or we can say it has the ratio of half, or it's the geometric series, right? Geometric series, geo series, ARn minus 1, right? And the S, we can conclude this is A over 1 minus R, right? It's half 1 minus half is 1, right? So it is converged. Okay. You can conclude this is converged. Okay, now the second one, let me just make it similar but different. So the next one is the 1 over 2 with the power of n plus 1. Is it converged or diverged? 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 Any guess? You can try and guessing. Converged or diverged? Converged. Okay. You intuitively say it's converged because it's less than before, right? So let me write here. 1 over 2 with the power of n plus 1. It's, of course, it's less than the previous one. Okay. And if the previous one, we say it's converged, then this also converged. So this is called the direct comparison test. So it's called the direct comparison test, or let me write here. Direct comparison test. Okay. So whenever you find any converged series, like for example, the right part here is converged, right? So whenever the series is less than the right part, the series on the left should be also converged. Okay. But you need to prove that it's correct that it's less. Okay. If you cannot prove that it is less than the known series, then you cannot use the direct comparison test. So whenever you find, you can directly compare the converges or the convergent series, then you can conclude that this series on the left is also converged. Okay. Let me write the theorem for the direct comparison test. Suppose you have A and B and two series. So series with positive terms. If Bn converges and An is less equal Bn for all n, then An also converges. And if the An, oh wait, wrong, Bn. diverges and an is greater than bn for all n, then the series will also diverge. Okay. 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 Now, still 11.4. Now observe is converge or diverge. Okay, so now you have 1 over 2 with the power of n and then minus 1. The question is it converge or diverge? We know from previous example that if you have this, it's converge, right? Let me write this is this converge. Converge the direct comparison test, it should be less than this. Is it correct? No, right? No. So it's actually greater. So is it converge or diverge? So we cannot conclude. Okay, we cannot conclude. Okay? We need another way to solve this. Let me write first the theorem and then go back to these questions. So this is called the limit comparison test. Let me write the a n and the n. Both are the series is with positive terms. So if the limit okay, a n over b n is equal c, and c is a finite number, and c is greater than 0. The conclusion then, either both converge or both diverge. Okay. Now going back to the previous question. Okay. Converge or diverge. Let's say we can write an is this, and let's say we compare to bn is this. Okay. To use the limit comparison test, we can write the limit. And then write down the formula for the series. Okay. Now we can solve this limit, right? So it's equal 1. Okay. So the limit exists. Okay. So to to determine the limit converge or diverge, we can write down because this is converge, right? Because this converge, and limit is equal 1, then this series is uh, is also converge. Okay. So when you find the limit, okay, you find the limit is having specific like this. Oh, it's 1. You cannot say directly, oh, it's converged. You say it's the limit exists first. Okay, limit exists, and then because of the other part is converged, then the other one also converge. Okay, that's the necessary steps for this limit comparison test. This limit comparison test is one of the tests that is frequently used. You will use this frequently because it's not too difficult to try. And what you need to do is you just plug in AN and VN. Okay? And you can think any series that easy to follow, okay, to be compared with. Okay. But if you want to compare, you can start by compare directly first. If it is no conclusion, then you can go here to compare. Okay. And find the limit. If it is a number, then the limit exists. So it can be both differ or both converge. So you need to find the other series. If the other series converge, then the problem will be also converge. If it is diverge, then it's also diverge. Okay. Okay. Any questions? I think I can add some of 11.5 parts. Okay, just a few, and then we can finish. Okay. So 11.5 is the alternating series. Let me write example for the alternating series. So the alternating series, if you see the number here, I have two series, 1 minus half plus minus plus minus plus minus. If we are taking this series as a distance, okay. So first we are going here plus 1, right? And then we are going back minus half, and then we are going positive plus here, and then going back 1 over 4 and 1 over 5 and so on and so forth. Okay. Now the same way, the second formula will be also minus half and then plus 2 over 3 minus 3 over 4. So it's going back and forward. Okay. So going forward, going back, going forward, going back, going back. Now, eventually, if you see how the arrow movement, how the arrow moves, okay, it will approaching something, right? Okay. Now, uh, the 11.5 is our method to show that, okay, it will be converges into some value or maybe not. Okay. But first, maybe we can write the formula for the the series. Okay. Every time you have the alternating series, you can factorize this -1 first. Okay. And depends on which terms is positive or negative in the first part. We can determine how the alternate series will have in the formula. From the first one, I believe it will be n minus 1, okay? And then 1 over n. But it can be other also, but I will choose this way, okay? It's easier to approach. The second formula, -half plus 2 over 3 minus 3 over 4, etc. It will be, because it starts with the negative, then we can say it starts from n, and then the n over n plus 1. Okay. So when n is 1, it's 1 over 1 plus 1, so it's 1 over 2. So -1 over 2. Okay. So for the how to find the formula for the sequence or series, I hope you can get familiarized. So I don't need to repeat all this formula. Okay. And now the important thing in the alternating series, as I mentioned before, you will arrive at the convergence value. So if the alternating series let's say you have this Bn, let's say it's B1 minus B2 plus B3 minus B4 plus dot dot dot. And this Bn should be greater than 0. If this satisfies, The first is Bn plus 1 is less than Bn for all n. And second, if the limit of Bn is equal 0, then the series is convergent. Okay. Now I think I will stop here. Any questions? Rather than we can just finish until here. There is actually another part about estimation, but I think I will maybe next time we will discuss that. Okay. If there's no question, so we will finish here. Hmm. Ya, ya enggak. Ini pokoknya selama ada uh, si angka yang setelah dari yang pertama, ini bakalan dia akan selalu lebih kecil. Jadi gini-gini, kalau dia selalu lebih kecil, yang angka setelahnya lebih kecil dari yang sebelumnya, berarti dia masuk kategori ini.